So, okay, so hi everybody, and I would like to welcome Alex Kelly and Alex Ororbia to this webinar about vector symbolic architectures and hyperdimensional computing. So without any further delay, I leave the floor to them so to introduce their talk.
Well, hey everyone, thanks for coming to our talk. So the title is a predictive processing implementation of the common model of cognition. And I am Dr. Alexander Ororbia, assistant professor in computer science at Rochester Institute of Technology.
And I'm Dr. Alex Kelly. I'm an assistant professor at Carleton University's Department of Cognitive Science.
So basically, the kind of fundamental premise that drives a lot of why we're proposing this architecture is a problem related to a model that probably all of you are quite familiar with, especially from the machine learning world, artificial neural networks, which basically are a type of statistical learning model loosely inspired by neurons and synapses in the brain, and are usually designed to process large quantities of data in the effort to extract patterns. Of course, this has often been called deep learning, or where we build essentially artificial neural networks with many layers. So they are very complex and can learn and approximate very nonlinear functions. The idea is that they can also handle naturalistic continuous value data, and in some cases they can process discrete data if we're dealing with, for example, text representations. But the idea is that the problem is that they're not typically used to model high-level cognition, and they're focused on being trained to essentially model expertise on a single narrow task. And while this has worked quite well, leading to state-of-the-art breakthroughs in, for example, image classification and speech recognition problems in the field of statistical learning, these neural networks are rarely trained on multiple tasks in a sequence. And there's a classical problem that prevents this from happening, known as catastrophic interference or catastrophic forgetting, which is essentially the problem where you take a neural network, you train it on some data set. Let's just focus on images and classification as a simple problem. Let's say we train a neural network to classify dogs versus cats on one data set. You give it a bunch of data. It learns to do that pretty well, high accuracy. Then we move on to a different data set, taking that same neural network and have it, for example, start to predict whether this is an airplane versus a truck. Give it a completely different data set, and the neural network will do very well on that second data set, but when you measure its performance on the first data set, it plummets to essentially zero, or it plummets to abysmal performance, essentially indicating that the artificial neural network does not retain any memory of its previous tasks, which is quite in contrast to human memory and human cognition, where we might suffer from slight forgetting in certain cases, but when you learn to do one task like riding a bike, you don't forget how to breathe. And so this is kind of the fundamental problem that motivates the cognitive architecture that we propose to attack, or to propose to construct, built on different pieces of building blocks that Dr. Kelly and myself have worked on in different research and complement to essentially combat this problem.
So on the other hand, there's this classic divide of neural networks versus symbolic architectures, which we're all quite familiar with. But symbolic architectures are, they're known to capture the complexities of high-level cognition, but they scale poorly to the naturalistic, non-symbolic data of sensory perception or to the big data sets necessary for modeling learning over a lifetime. So is it possible to provide a theory that bridges neural and symbolic models while retaining the strengths and capabilities of each? We're of course going to propose using vector symbolic architectures. That's why we're here. More specifically, we're going to be combining neurogenerative coding, which is Dr. Ororbia's expertise, with holographic memory or vector symbolic architectures. And we're going to try to bridge artificial neural networks and symbolic models, combining the advantages of each in the form of a cognitive architecture that can capture human performance at all scales of learning.
Do you want to?
Yeah. So cognitive architectures serve as unified theories of cognition and computational frameworks for models of specific tasks. And 40 years of work have developed hundreds of cognitive architectures with strong commonalities, suggesting an emerging consensus on the principles of cognition. On this consensus was proposed a common model of cognition, a high-level theory of the modules of the mind and how they interact. The common model consists of perceptual and motor modules that interact with the agent's environment, a working memory to hold the active data in the agent's mind, and a declarative memory that holds the agent's knowledge, and a procedural memory that controls the flow of information and evaluates possible actions. So
now we bring ourselves to one of our key pieces to actually perhaps implement concretely different key elements of the common model of cognition. So what we have here in the diagram to the right is a few of the blocks, which essentially there are 5 key blocks that the common model of cognition specifies. The 3 that are in pink at the bottom is where we propose using our work on neural generative coding to actually instantiate this as a part of an actual living, breathing cognitive architecture that can process multiple data sets and multiple tasks. So the idea is that we center around another particular brain theory known as predictive processing. I've cited Andy Clark's work here, but there's plenty of work that actually starts around the 90s and before, actually can trace its roots even back to Immanuel Kant and Helmholtz. And the idea is that predictive processing embodies a particular Bayesian brain theory that at the fundamental simple level just says that we essentially process sensory inputs or sensory samples of our environment by first guessing them and then correcting ourselves based on those guesses. And the idea is that we are essentially learning stateful representations of our environment, whether it's reactive, where we're processing data and just trying to build an internal generative model of the world, or whether we want to drive something like action, which another aspect of predictive processing, some of you are familiar with, known as active inference. Carl Friston and Buckley and many others have been proponents of it. And recently, some of our work has shown actually how to instantiate concretely in a machine learning based framework how to take the active inference framework and actually combine it with ideas of predictive processing, specifically predictive coding, which is what brand that we bring to the table called neurogenerative coding, which is effectively just a scalable particular version of predictive coding that can actually be implemented and takes care of a lot of problems that center around the common algorithm used to train deep neural networks today, which is known as backpropagation of errors, which is often heavily criticized for its lack of neurobiological plausibility. You can move on to the next slide. So some of these biological motivations, the idea is that backprop imposes a ton of constraints and a ton of issues that would be difficult, or perhaps we have not found any evidence in actual cortical function or actual function of real biological neurons to support what it asks for. Namely, the idea that in backpropagation, we take a big neural architecture, we have maybe perhaps an input layer or something else, and then we have an output layer that makes a prediction. We usually specify a cost function or an error measurement at this output layer, and the idea is that to change and adjust the synaptic parameters or weights of this grand architecture, we have to use the chain rule of calculus to essentially calculate the derivatives or the gradients of the actual error cost function at the very output layer and essentially transmit this information along a massive global feedback pathway, essentially using the forward connectivity that was defined by the architecture to reverse the direction and transmit information related to these derivatives. On top of that, we have to use differentiable activation functions and know their pointwise derivatives as well, which again has argued to be a problem for implementation in hardware. And there is not necessarily evidence, or at least massive evidence, to support that neurons know their exact pointwise derivatives of their activity as well. And of course, backpropagation is well known to create practical issues such as the exploding and vanishing gradients. And the way that we usually combat them in the machine learning community is by introducing all kinds of constraints that can actually further limit what you can actually put inside your architecture. Notably, things like non-differentiable activities. If we want to use stochastic functions, we have to work really hard to bend the architecture in a way to allow this. Lateral inhibition or lateral synaptic matrices are very difficult to implement in most architectures, given that we need a directed graph. You can use, for example, a recurrent network to model such a thing, but now we have to do backprop through time, which is even worse than backprop, as that would require taking your brain and stretching it backwards in time to then compute the derivatives of every synaptic weight and add them up to get your actual gradients. So already from that point of view, we would like a neural architecture and learning algorithm system that avoids these problems. And that's where we get into the predictive processing part. It is known that the brain does multiple steps of processing. There's at least sufficient evidence that when we process something, we're usually actually processing even an image across time. You could think of, for example, your eye movements. You're not just looking at one thing in one instantaneous moment in time, hence indicating that perhaps neurons in the brain have some stateful aspect to them. And essentially, this is what would allow the passing of bottom-up and top-down messages to do that error correction that I mentioned in the slide before, where we're doing guess, predict what's in our environment, and then adjust it. This framework actually, ultimately, when you dig into the literature, opens itself up to local learning rules in connection to Hebbian learning, which is arguably a little bit more biologically plausible for modeling synaptic adjustment. And of course, we have plenty of evidence. There's a lot of current evidence in neurophysiology and neurobiology that actually supports pieces of the predictive processing account. It's not perfect, and we still have a long way to go, but it's encouraging to see this this evidence come about. And again, we also have some nice theoretical grounding. I'm not going to reread that bullet point, but Rao and Ballard introduced the kind of heuristic form of predictive coding in 1999 as one of the more well-known models. And then Carl Friston, 2005 through 2010, essentially reformulated it and connected it to the beautiful framework of Bayesian inference, essentially showing that the model is doing approximate Bayesian inference when you're actually minimizing something called the free energy. And another point that I just like to throw in here is that we argue that sparsity is critical, particularly to combat catastrophic interference. There's a lot of nice classical work that used to talk about non-overlapping representations and sparse distributed representations, including, for example, models like sparse distributed memory, where the idea is that you can reduce crosstalk by having very few neurons activate in the response to a pattern. And usually these neurons correlate to something very unique about maybe perhaps they're correlating to a particular object like a circle or a square. And you don't want necessarily those neurons to be reused across those objects. And so if we could actually learn sparse representations, we could actually prevent their overlap, thus preventing, for example, overwriting of synaptic weight values. And we'll talk a little bit about some of the ways we've been implementing that in some of the work that supports our cognitive architecture. Can move on, Alex. Yeah. And again, this is just to illustrate what I was just saying in the last slide. I don't know if anyone can see my mouse, but it's fine. At the very top, we have backpropagation of errors, where let's just say we have an arbitrarily deep feed-forward neural network. At the very left of that diagram, we see E0, which is just to represent a vector of error neurons, or actually you could calculate them as the first derivative of some cost function. And then, of course, we essentially move this information back along the network, along those red arrows, And again, we're stylizing things. If we wanted to actually dig into the mathematics, we can talk offline. But the idea is that we would, multiply things by the activation derivative, and then essentially do matrix multiplications with the forward synaptic matrices to go back to Z0, Z1, and Z2 to get the gradient or the derivative of the cost function with respect to that particular activity layer. And then we can do another extra multiplication, and now you can calculate your actual gradients of the weights. Whereas in the middle diagram, we see neurogenerative coding and how it would formulate the same type of model. We would have an arbitrarily deep network, but perhaps now we say that Z0, Z1, and Z2 are actually perhaps the mean prediction values of stateful neurons that are actually those little circles. Like, for example, we'll see to the little blue dots, like E1, you'll see to the left another circle. Those are the stateful neurons that hold some activity value, and these are used to generate a prediction labeled as Z bar 0. And effectively, that's going to be compared to a target. Let's say it's pixels of an image, and we can calculate the error through a mismatch signal. And then, of course, that mismatch signal can be used right away to update the weights, for example, that connect Z bar 0 to the circle to the left of E1. I should have labeled it as just Z0, but forgive me for that. Same thing for the inner layers. They don't require waiting for the error signal at the very output. If you'll notice, now that we have an E1 and an E2, all we have to do is have, for example, the little circle to the to the left of E2 serve as another vector of neurons that hold their state. They generate a prediction, Z1 bar, and that is compared to the actual state values to the left of E1, which would just be Z1. Yeah, since you're sharing the screen, Alex, you'll have to move your mouse if you want to show that. And the idea is that mismatch signal can be calculated quite easily. In fact, all these layers can generate their predictions, calculate their mismatch signals, and update their weights in parallel to each other, essentially just using a simple error-Hebbian rule, which that reference to the left, Ororbia and Kiefer 2020, showed one way to do that very cleanly and scalably with a generative model. And of course, the very bottom diagram taken from Frist in 2005 just shows a mapping, one possible mapping to actual pyramidal neurons and other aspects of synaptic circuitry where these forward predictions and backward predictions actually might lie, for example, in the visual cortex. Now, move on to the next slide, as we should keep going. So what I have here is just a brief series of 3 images. I'll tell Alex to move on to the next one by saying next. What we see here is, let's just say we have a very simple generative model. At the very top are just 2 stateful neurons, the middle are another 2 stateful neurons, and at the very bottom are another 2 stateful neurons that would be clamped to, let's just say, a pixel image with just 2 pixels. Keep it very simple. Now, the neurogenerative coding process, very simply and in a cartoon formulation, read the reference Ororbia and Kiefer 2020 for the actual mechanics. The idea is that these stateful neurons first have to do one step. They have to laterally inhibit and excite each other. So that's what we see, for example, at the very top. You'll see these little arrows with the diamonds, which are essentially to represent, for example, excitatory signals, or inhibitory signals. And then the curves with the little open circles are to indicate inhibitory signals. And the idea is that these neurons, since they have values, they might be initialized at 0 or some random value. Usually we keep them positive to keep the activities positive. They will transmit information to each other and essentially form a sense of competition. So the idea is that these can be formulated as another matrix called a lateral synaptic matrix. And the idea is that you can encode very specific values to actually have these neurons inhibit and excite each other such that you learn very naturally sparse distributed codes. And the idea is that these stateful neurons, which you'll see them in gray, have, again, a set of lateral synaptic matrices, lateral synapses in the middle and at the very top. At the very bottom, since those are just clamped to the input, we don't necessarily need to model that, but you could. And the green diamonds are the error neurons. So remember, E bold in the last slide was just to indicate a vector of neurons. So here we propose a one-to-one mapping that is biologically implausible, and that can be resolved. See the paper for ways to do that, but a very simple version of this model requires these error neurons, one to every stateful neuron, and the idea is that they're going to compare a prediction generated from the layer above to the layer that they are resting right above. So the idea is that, let's say, the middle layer will generate a prediction of the input layer at the very bottom, and the very top layer will generate a prediction of the middle layer. And those green diamonds are meant to compare the predictions generated from that layer with the actual value in those gray circles. Other key point just to note is that these error neurons are also laterally connected as well. And this is taken, for those that are familiar with the free energy framework, we chose to model with our own approximation of something called a precision weighting. And the idea is that that's another matrix that, again, multiplies the activities, but this is a multiplicative interaction. And the idea is that you can actually encode, for example, inhibition and excitation in this framework as well. But the idea is that this will serve as, for example, in a simple implementation, as the covariance of a multivariate Gaussian. Again, see the paper for those mathematical details that we won't go into in this talk. If you click the next slide, Alex, you'll see what happens next. So once those neurons have fired their signals to laterally inhibit each other, you'll see that now the originally kind of lighter colored arrows are now dark. These are actually the predictions generated from each particular layer. And you'll also see that, for example, they're going to create an excitatory signal, which is what, again, those filled in diamonds represent. And they are just essentially, a matrix multiplication of the activity of the layer above. They will generate, for example, two values. But you'll notice that the stateful neurons underneath every error neuron will also transmit their signal up as an inhibitory signal, which essentially creates that subtraction or the mismatch signal that we would want, which approximates roughly actually the first derivative of a cost function. You could argue it's the cost function of mean squared error that you're calculating roughly the derivative of every layer. It could be more complicated since we introduced lateral weights that you essentially are dealing with a multivariate Gaussian. And so there's work that shows that, for example, this type of model is a deep hierarchical Gaussian model. If you click the next slide, Alex, what happens next is then once we have those green diamonds updated, right, we have now had to calculate the new mismatch signal. Remember, those neurons had to originally be initialized to something like 0 because we didn't have any activities calculated at the very beginning of simulation. We now pass this information back along the network with those dashed arrows, which are another set of weights, actually more of a hallmark of our predictive coding called neurogenerative coding, that will called error synaptic weights, or recurrent weights that actually will transmit through multiplication that information back to their respective layers. And of course, those green diamonds need to affect the states right underneath them, so that can be carried over with just even an identity connection. And the idea is that this will now be used to create a perturbation that will then adjust the synaptic activities of those gray circles. So whatever activity those gray circles were before we started this cycle of 3 images, they're going to now change. And the idea is that except with the exception of the very bottom 2 circles, which normally we would clamp them to sensory input or something we've observed in our environment, these other stateful neurons will cycle through this process that I just showed you in 3 steps multiple times. Again, they can be parallelized quite easily. And the idea is that this will cycle until it relaxes into a sparse distributed activity for both those layers. And the idea is that this representation is roughly a maximum a posteriori estimate that is causally explaining the input, or at least you could just argue it's searching for a representation that sufficiently explains whatever input it's currently found. And again, all the mechanical mathematical details are provided in the references throughout this talk. If you go to the next slide, Alex. Also here, I just show very briefly, we don't need to dwell into the actual synaptic matrices values. This is actually what a neural circuit would look like if you zoomed in on just one error neuron in just one stateful neuron. There's quite a little bit of synaptic connectivity going on here to demonstrate, for example, self-excitativity. And of course, those actual gray boxes or gray squares actually are better to indicate the multiplicative interaction. As the error neurons move across time, they have to multiply by their previously known stateful values. But we can move on. We don't need to dwell on this diagram. And again, this is just another stylization of the same thing we just saw. One key feature I just want to mention, this is actually taken from more recent work where we actually took this architecture and adapted it to do reinforcement learning under the active inference framework. The very top layer, you'll see Z2. You'll notice I have it set equal to X, which might give you a more sense of familiarity with a deep feed-forward network that we are familiar with in deep learning. The idea is that you can clamp any of these states to activity values that you desire, and then just force the neural generative coding network to cycle through its activities until it finds whatever pieces are missing that you didn't clamp it to, such that they please this mapping. So basically, this architecture would only use that three-step process I explained earlier and cycle through that a couple of times, usually about 10 to 50 different steps, depending on your simulation. And the idea is that it would just alter Z1. So those two boxes in the Z1 layer, it's going to adjust those values until Z2 accurately predicts Z0. What's really nifty and something that I'm kind of like glazing over these details so we can get to the rest of the talk is that those synaptic weight matrices, which are those straight arrows, they're very easily adjusted because we have E1 and E0 and Z2 and Z1, which are essentially the only vector activities that we need. We can just do essentially dot products or matrix multiplication or matrix vector multiplication between those two vectors to easily and quickly calculate the Hebbian update. This is really not quite a legit Hebbian rule, since Hebbian rules often take the post activities of all the layers and kind of do something with that information. This we usually call it an error Hebbian rule. It might remind some of the delta rule, some of the classical rules when we were training neural nets before just using calculus and reverse mode differentiation. And the idea is that these rules are very quick to compute because you'll always have the activity E1 and Z2. You can literally update the synapses at any step in time. I guess the last point, I'll just repeat myself, is that those steps that we showed earlier, they are part of a cycle. So you have to run through those calculations multiple times, which means that the neural system has to look at Z0 or the actual image that's presented to it or whatever the sensory input. It could be a waveform, it could be a text document. There's no necessary limitation to what type of data you can process. The idea is that this model needs to run on a time scale to actually find the right activities to explain that input. You could also, if for those of you that like differential equations, you could argue our cycle is very similar to Euler integration or an approximation of that. We can talk more offline though as well. If we move on, Alex. So the idea is that that framework, that neural generative coding framework, can be used now to implement particular circuits that we want to use in our common model of cognition. So to deal with perception and action, since we're going to need, for example, to model something like the motor cortex to drive an agent or a system to actually do something and interact with the environment, we propose, for example, combining working memory and using neural generative coding. So working memory, Alex will give you details about the holographic symbolic memory that we propose to do that. But the idea is that if working memory can produce an vector activity or set of vector activities, we can actually couple it to our neural generative coding models, which I argued already in the previous slide. You can clamp to any layer, any particular input values you want. That doesn't have to be data. It could come from the output of some other neural system. And we need to model, for example, a perceptual cortex or a modality cortex, as I call it. So if we're processing pixels, we're going to want a neural generative coding model to model, for example, roughly the visual cortex. If we have an auditory cortex, we'll also use a neural generative coding model to model that, and whatever modalities we need to process in our cognitive architecture. And then we need to do a motor cortex. So while the mechanics of actually how we can adapt NGC or neural generative coding to do that is quite involved, and I recommend also reading the reference Ororbia and Mali 2021 for exactly how to do that and some benchmark results I'll show you briefly next. The diagram to the very right shows again, like let's say we have a working memory system, it can produce an extra value and we can actually calculate, for example, the memory value stored in working memory and alter, for example, something like the predictions that are being generated, or sorry, the stateful neurons, which are kind of those like little gray box, sorry, those white rounded boxes. And the idea is that these can be modified by working memory and the mean prediction of the layer above. So again, these diamonds, for example, are representing error neurons. So we need to have another system. So we have here, we show a little tiny complementary system. We have essentially a working memory system that just, let's say, produces a vector activation. And we have a neurogenerative coding network at the very bottom, which we're calling loosely the visual cortex. So a very simple model. We're not modeling accurately V1 and V2 visual cortex areas. We're just representing it at a high level of abstraction. And the idea is that this model will learn to do a mapping between pixel values at time step t, produced by a simulator like an environment or something perhaps that a robot gets. And it learns to predict what it thinks the environment's state value is going to be at the next time step t+1, which is what x of t+1 is. And the idea is that these errors can then be used to transmit signals to another neurogenerative coding network that is very specialized. It might remind some of you of a Q-learning network. The idea is that this network is conditioned on x of t, and its goal is to predict an action or to generate an action. Now, of course, its objective ends up being a modified form of the Bellman equation, which we can actually take the error neurons and have them approximate what's going on there. And of course, the neat thing is this connects to active inference, and I'm, again, glazing over a lot of mathematical underpinnings for these just for the sake of moving on, but we would have two terms. The idea is that the bottom model, which is our visual cortex generative model, guides the exploration of the agent. So now instead of like typical reinforcement learning where we have to randomly flail around and try to understand our environment, we can actually drive a more intelligent form of exploration through the errors calculated from our generative model. The worse our generative model does, for example, let's say it predicts x of t+1, it could be pixels of an image of a race car, and it gets it really wrong. The idea is there's high surprisal. So this is very surprising to the network, which means it's going to have a very high epistemic term, which I'm borrowing from Friston's active inference framework. And that can be combined with an instrumental term, which is usually a goal-directed term. So we obviously want the agent to maximize its rewards over a horizon. So that could be something you use as an instrumental term. Maybe some of you are Bayesian and like to design prior functions over goal states. You could also do that and work in the log likelihood of your prior distribution in there. You could learn this through imitation learning. There's a whole ton of options there, but the idea is that these two terms combine together and alter what we would call the controller or the motor cortex, which essentially is what's producing our action. You can move on to the next slide, so that way we just move on. And again, this is just another schematic of kind of showing what just this little generator visual cortex model and the controller model or the motor cortex do together. Let's move on for the sake of time, but the idea is that this system actually would work on an observation at time step t and try to either predict the next time step observation and, of course, generate an action which will influence its environment and change what observation it's going to get. This agent, effectively, what it will do is it tries to minimize its surprisal. It wants to understand just enough of its environment such that it can reach its goal. Because remember, there are two terms, instrumental and epistemic, so it's balancing exploration and exploitation the entire time. So it doesn't do a brute force search of its environment. It is literally trying to understand enough of its environment such that its action policy can actually guide it to the goal state or goal states as quickly as possible. Alex, you can move on. And again, these are just some nice results. I mean, we can revisit these maybe towards the end of the talk for those that have questions, but we show that actually this system works quite well. The blue curve, just quickly, is actually our ANGC agent. Since then, we've actually done some additional results where we've actually done some ablations, but the idea is that it actually performs quite well and competitive with even, for example, a deep Q network trained with backpropagation using a special entropy bonus, so that way it was a more fair comparison comparison, so it had more intelligent exploration. And what was neat is that in these results across these classical reinforcement learning problems like the cartpole task, which is the first one, mountain car, or guiding a lander and trying to guide it to land cleanly and softly in between those flag posts that you kind of can see there, the two yellow flag posts. It turns out the agent worked really well. It actually learned very quickly with a lot less data, which is a very nice thing for like model-based reinforcement learning, and it was stable. As we found with a lot of these architectures, if we wanted to make, for example, a deep Q network stable, you have to introduce a ton of heuristics and train it for a lot longer for it to converge to a more stable policy, whereas ANGC, or neural generative coding from an active perspective, works very well and very stably. Move on to the next slide. We also did, for fun, we also did a robot arm task. Again, these are all simulations, so this is all software side. We haven't actually implemented it in hardware. And again, the ANGC does a lot better than all the other baselines, and it's quite stable, which was something that we really liked about that result, because if we were to use this motor cortex, modality cortex interaction in our cognitive architecture, we would want the system to converge stably to certain policies as it finds the information it needs when it's exploring, perhaps, for example, exploring a maze. Go to the next slide. So the other part, just to make sure we fill out the common model of cognition, we have our motor cortex, we have modality cortices, which are really nice. And we are just missing the procedural memory, which we are focusing currently on. Well, procedural memory can be argued to come from other sources, and other neural systems can play this role. And we don't want to necessarily say that those hypotheses are wrong, but it is argued that the basal ganglia does a lot of this information routing that Dr. Kelly explained to you earlier. And so actually we've had some work that demonstrates how this can be exploited to build a neural system in machine learning that actually is quite robust to catastrophic interference, which is one of the problems we talked about really early on that motivates our architecture. So the idea is that in our cognitive architecture, again, working memory would provide additional signals, which again, working memory would be guided from declarative memory, and I'm keeping those connections kind of vague, but the idea is that this information is going to condition our agent depending on what the working memory state is as well and what declarative memory wants to do. But just to zoom in at the very bottom, we sort of see two rough neural models. We see this very simple one to the left that's kind of spewing out those curved blue and curved red arrows. That's roughly, let's just say, a simplified version of the basal ganglia model. And the way that we approach this in the machine learning world is we condition the basal ganglia model on just a sensory input, so it receives some stimulus signal. And the idea is that this basal ganglia-like model, which also, by the way, I'm keeping some other details buried. It's learned through competitive learning, which is another form of classical neural learning, which is kind of roughly Hebbian. The idea is that this system will generate signals or command signals to the modality cortices. So in this case, I'm showing two cortices, one in light blue, the light blue box, and the light red box. And our modality cortex would actually shut them off. So in this case, we're just representing red as a signal that's saying, turn this off. We don't need this neural system or this set of neural resources, but the blue we want to use. For example, let's say that the basal ganglia model decides that we're processing visual input and we don't need all those neural resources for the other modalities. So I'm going to laterally inhibit all those neurons such that their activities are suppressed and they go towards zero, since we usually deal with positive activities. And I'm going to excite or at least gate and say that the neurons in the blue system should be used, because that's what we usually use when we're processing, for example, cat images or dog images. And of course, this inhibition system goes a bit further than just the modality. It actually, what we did was we focused on, in our work, if we move to the next slide, we focused on just the modality cortex and actually inhibited subnetworks inside that network itself to prevent catastrophic forgetting when we're learning, let's say, cat and dog images versus airplane and truck images. And so roughly we have a schematic here where, let's say we're receiving a data stream over time. Now, these are just static vectors. This framework can be extended to temporal data. It can be extended to the reinforcement learning regime, roughly through the ANGC framework I talked about earlier. But let's just say we have our little basal ganglia model, which we're calling T of X. It's stimulated by some input, but it doesn't have any knowledge of, like, for example, the supervised label or the task that it's doing. Its job is to decide how to route the information and drive parts of our generative model, which now is just one cortex or modality or visual cortex, and it will stimulate different neurons in different layers and shut off others that basically say, you're what I need to process this image of, let's say, the cat, this particular cat, I want you to use these resources, and I'm going to adjust the synaptic weights that relate to those very specific neurons. And so over time, of course, this neural basal ganglia model kind of learns to separate out different tasks, and it allocates, for example, its own neurons to say these are going to trigger these neurons in this other neural system. And since it's learned through competitive learning, it turns out that learning algorithm works really well for preventing a lot of crosstalk that I mentioned we wanted to get rid of. And of course, ultimately, what we see in the system is as we're processing data like X1 and Y1, X2, Y2, X3, and Y3, this generative model is learning to adjust itself at a subnetwork level and partition its knowledge and reuse knowledge. Because the neat thing is, let's say you trained on cat and dog images, and then you trained on planes and trucks, and now I give you another data set of cat and dog images. Well, the typical neural network, especially in the deep learning world, would still catastrophically forget everything it's seen before. It has no idea that it actually was ever exposed to cat and dogs before, and it'll just start learning that as if it's a brand new disjoint task. Whereas the basal ganglia model would be able to say, wait a minute, I've recognized this system. These go to these neural resources, so we can just keep adapting these particular memories or these particular synaptic weight values for that particular task. And I show some symbols here to the right, but we don't need to worry about that. The idea is that we just know that we have a big pool of neurons, and out of them are going to emerge a very sparse, tiny network that's, again, a neural generative coding network specialized for processing a pattern of that particular task. If we move on, Alex, just to show them just quickly. We don't need to go over all the lines in this table, but it just turns out when you build a system like that, you end up reaching roughly state-of-the-art performance. At the very bottom in the blue box is roughly that architecture that I just explained with a simple basal ganglia and a visual cortex model learned through neural generative coding and some competitive learning. All those rows above it are backprop-based, state-of-the-art, lifelong learning models that have been designed, which basically introduce all kinds of heuristics. Oftentimes, they use data from previous tasks, which kind of violate the idea of a cognitive principle, which is we don't get access to exact copies of the universe that we once saw. We're living in a stream, so whatever you get right now is what you have to deal with, and you'd have to use memory or memory replay to, for example, deal with things in the past. A lot of these models actually use physical data and they store them in a buffer. Our model doesn't do any of that. And a lot of these models too, especially the ones above the middle, like black line, like RTF, DGR, these actually use knowledge of the task. So essentially, the human has to play the role of basal ganglia and oftentimes has to say what's going on. And many of these models depend on some type of human input to actually learn different tasks, whereas our model learns those tasks and those task separations completely itself, guaranteeing that when it transmits those signals to those visual cortex, it actually is done through another matrix, which is through lateral synaptic inhibition and excitation, which yields sparse codes. And we know from a lot of good work on competitive learning, classical work on competitive learning, classical work on sparse representations, that we can actually get very, very compact codes that have very little overlap. And so, again, that opens the door for even coupling these systems to memory systems, like, for example, sparse distributed memory, and learning to manipulate those vectors and using those to gate different aspects of the neural generative coding model. And I just wanted to plug that in because some of you work on those different types of models, and it kind of leads to where we get into Dr. Kelly's work. You can skip the next slide. It's just another benchmark that also shows that this does better than all the backprop stuff. And that's end of the neurogenerative coding part.
All right, so the common model of cognition consists of, it's got perceptual cortex, visual, like sensory cortices. It's got the basal ganglia that handles sort of procedural memory. And Alex has talked about each of those aspects. And it's quite an impressive agent you end up with when you implement it using predictive coding and forms of Hebbian learning, competitive learning, and error-driven Hebbian learning, that it produces state-of-the-art result. It's this sort of little animal that does extremely well on these tasks, but it is an animal that doesn't really have much in the way of memory. We don't know yet what this creature will behave like once we've hooked memory in, because we haven't done it yet. But I'm going to talk a bit about my area of expertise, which is models of human memory, and the models specifically that we're thinking of hooking up to this predictive coding neural network to see if we can produce not just a implementation of the common model of cognition, but also a model that can model human and animal behavior and be an impressive intelligent agent on artificial intelligence tasks. Did I skip a slide? I want to double check that. Okay, yes, I think I did skip a slide. So we're implementing now the declarative memory and the working memory. And I'm going to use the term holographic memory fairly interchangeably with vector symbolic architectures, hyperdimensional computing. Like this predictive coding model, holographic memory is immune to catastrophic interference. It can learn multiple distinct tasks. And it is also based loosely on Hebbian learning, and that is a compressed form of Hebbian learning. And it is, as we all know, it's biologically neurally plausible. So we can use it to do working memory, and we can use it to do declarative memory. For working memory, the way we're going to think about working memory is that each working memory buffer is a holographic vector. And vector symbolic architectures have very long established ability to model serial of free recall of lists. This includes Bennett Murdoch's totem model, which goes back to the 80s. More recent work includes Franklin and Newhort's 2015 model, which is shown here. The model against human behavior on a immediate recall task and final recall, free recall tasks. And also Stefan's talk is an exciting new model of working memory using vector symbolic architectures. I haven't committed yet to a particular vector symbolic working memory model. We'll probably play around with finding what works best with predictive coding. But there are a number of established models out there. I'm probably just going to grab one and adapt it for a particular task. Declarative memory is something that I've been working on for a while. So I have a model of declarative memory called holographic declarative memory. And it's going to consist of many holographic vectors. It's maybe a bit like sparse distributed memory. However, I'm using holographic reduced representations, so they're not sparse. I could possibly switch to using sparse vectors. I don't have my heart set on a particular type. Holographic declarative memory is based on the Beagle model, which captures semantic priming and word meaning. Holographic declarative memory captures human recall, probability judgment, and decision making. And you can also see my other talk in this VSA webinar series for a version of this model capturing part of speech. Okay, so in the current HDM, stimuli are encoded as slot value pairs. So if you have a stimulus that's a large black square, it would be color black, shape square, size large. From there, we construct queries, essentially a set of questions you could possibly ask about the large black square, like what color is it? What shape is it? What size is it? Each of these queries is then assigned a set of vectors that represent the query. In particular, slots are represented by permutation. So to do a slot value, you permute a vector with the slot. Then you do a convolution and summation step, and then add to memory. During the convolve step, all n-grams, all combinations of permuted vectors are summed together. This isn't the only way to encode information into the memory system. The other approach that I've already used is just have a linear sequence of symbols. In this version, instead of having slot value pairs, there's just a single permutation, p before, which is used to preserve order, and it's applied repeatedly in a nested fashion to create the queries, which are then assigned to memory. Now, this isn't terribly, this is very limiting in the sense that it can only represent sequences of symbols or slot value pairs. But Brent Comer's talk on neural representations of continuous space using fractional binding suggests that there is a way forward for using vector symbolic architectures, actually a very promising state-of-the-art way forward for using vector symbolic architectures with complex visual stimuli. So when I talked about the encoding step, I kind of glossed over the convolution and additions. So to do this, what we do is, let's say we wanted to encode large black box and we wanted to update the memory vector for black. We would replace black with the placeholder vector. This acts as kind of a wild card or fill in the blank. A concept memory vector is the sum of all questions to which that concept is an answer. So if you have large placeholder, essentially is the question large what? Or you can have what box or large what box. So for large black box, there are 3 possible questions you could ask about that where the answer is black. Large what box, or large what box. And all of these questions get added to the memory vector black. So this is the equation for it. We just translate each of those questions into a set of vectors that we convolve together, and then we sum those questions together into the memory vector. Now, integrating this with the neural network, you have to ask different questions like, what are the discrete symbols? Can we step away from discrete symbols? And how do we do this over continuous time? So there are real problems to solve here. So we already talked about, we can in fact encode complex visual stimuli using vector symbolic architectures. The discrete time steps thing might prove to be more of a problem. So I've used the holographic declarative memory in a couple of different things to demonstrate that it does capture fundamental principles of how human memory works. I'll very briefly go over those since we're running out of time. One of these classic memory experiments that it captures is the fan effect task. So the fan effect task is subjects see person location pairs, such as hippies in the park, officers in the store. And then at test, they have to determine which pairs they studied. So the fan effect is specifically the finding that participants are a lot slower to judge pairs that contain items that occur in more pairs in the study set, that is, they have higher fan. For example, if you ask the participant, okay, was the hippie in the store? This is actually really difficult if there were 3 facts in the study set: hippie in the store, hippie in the bank, and hippie in the park, and then 2 facts about the store: hippie in the store, officer in the store. So they have to sort through all these irrelevant memories to find hippie is in the store. So the theory here, and this is why it illustrates a fundamental principle of how human memory works, is that the availability of an item in memory is related to the item's probability conditional on the cue. So given the cue hippie is in the store, specifically the cue hippie, the hippies in the store, hippies in the bank, hippies in the park, there's only 1 chance in 3 of each of those being relevant to the cue hippie. Similarly with store, there's 1 chance in 2 that hippies in the store is relevant, and 1 chance in 2 that officers in the store is relevant. So officer in the store is going to be more available than, say, hippies in the park, because officer in the store has a 50% chance of being relevant, whereas hippie in the park has 1/3 chance of being relevant. And so this is just a fundamental principle of how human memory works. And this falls naturally out of the geometry of vector spaces. So if we consider the memory vector for hippie, after it's studied the study set, it'll be exactly between park and bank if there were only 2 facts studied about hippie. Conversely, if there were 3 facts studied about hippie, it'll be exactly between park, bank, and store. As the number of facts increases, the distance of hippie from any of its facts increases. As a result, the cosine becomes smaller, and then from the smaller cosine, the model predicts longer response times. So the cosine is approximately the root conditional probability item in memory given the Q. So that's one classic basic memory phenomenon that falls right out of vector symbolic architectures. Another classic is the conjunction fallacy, which is a classic finding about probability judgment. You show people a little story about a woman named Linda, who's a social justice activist, and then ask her, how likely is she to be a bank teller? How likely is she to be a feminist? And how likely she is to be both a bank teller and a feminist? Well, people are going to say, well, since she's a social justice activist, she's very likely to be a feminist. They don't judge her to be particularly likely to be a bank teller. In fact, they judge her to be more likely to be both a bank teller and a feminist than a bank teller, which is in fact impossible because according to probability theory, the probability of being both a bank teller and a feminist is lower than the probability of being a feminist and lower than the probability of being a bank teller. That's just how probability works. But we can predict this if you train holographic declarative memory on like a large corpus of text. And then you just ask it, is Linda, the sum of all words that describe Linda, more similar to bank teller or more similar to bank teller and feminist? And this is consistently the case. Linda is by cosine similarity more similar to feminist and bank teller than it is to bank teller. That's probably the judgment humans are making, is they're like, well, Linda seems more like a feminist, so she's probably more like a feminist and a bank teller. So they aren't really using probability theory. So based on this probability judgment capacity, I threw a holographic declarative memory at essentially what you can think of as a reinforcement learning task. It's one where participants learn to make choices between arbitrary symbols that stochastically yield positive feedback. So initially they press keys on the keyboard, let's say R and J. They get a symbol like a diamond or a triangle flashes up on the screen. Then they have to press 2 different keys, T or V, and then they either get a positive feedback good or a negative feedback bad. And there is an optimal set of choices here. The optimal choice is to pick J, hope that you get a triangle, and then to pick V if you do get a triangle, but conversely pick T if you don't get a triangle, if you get the diamond instead. And this is very difficult to learn because it's very random. But humans do gradually learn it across a long time of 400 trials. So we can implement this using holographic declarative memory. We can say there's a symbol for positive feedback. We're going to maximize trying to pick positive feedback. I experimented with a number of mechanisms such as punishment, which is if negative feedback is actually negative, which turns out would be more like you electrically shocked participants every time they got something wrong. Optimism and surprise, which is predictive coding, which is you make a prediction and then you weight things by the difference between the prediction and the observed outcome. What I found with holographic declarative memory is if you punish it, it doesn't learn the task. It just gets depressed because it's getting electrically shocked every time it makes a mistake. But if you make it optimistic, it learns the task quite well. And if you make it optimistic and do the predictive coding thing, it actually learns the task quite well at a level on par with a good human subject. So we don't have too much time at this point, but we've got a lot. We have a lot that we need to kind of figure out how to put together. Since the holographic side of things, the current implementation is on discrete symbols, it's not in continuous time either. So there's a bunch of problems that we'll have to get kind of solved along the way to hook it up.
And basically figuring out the proper way to merge the holographic memory vectors and the neural generative coding side of things as well. We have some rough ideas, and again, linear algebra lends us some tools to connect, for example, and multiply and transform the matrices and condition one model on the other, but the optimal way in which that wiring should be configured is also the immediate subject of what we need to figure out in order to properly build what we were thinking about building, for example, a kernel, to use an operating system term. And the idea is, for example, focus on just maybe working memory and wiring it up to a modality cortex and motor cortex and just seeing how that interaction works. And as we start to get promising results, take our cognitive architecture kernel and start expanding on it module by module until we have something that fills out each element of the unified model of cognition. Is kind of one approach that we're taking. And again, one of our interesting application areas that we want to look at is continual reinforcement learning. Since we have a motor cortex, we would like to use it. And so action-driven learning is one of our primary interests as well. And so this could potentially be very beneficial even to that domain of machine learning, as well to cognitive science that's interested in looking at how do we build an agent that learns and aggregates and uses knowledge across multiple tasks based on what we would argue is a fairly reasonable approximation of what's going on in our current knowledge of the human brain and memory. So, I mean, that's, I think, all we need to say here, Alex. I mean, that's pretty much it. Yeah. So if there's any questions, sorry.
Thank you very much. So huge applause to you. From the audience. So any questions from people here? So let's wait. Well, maybe I can start with my question. I'm sitting and thinking, well, actually, frankly speaking, I didn't read your paper, but definitely this is it requires a deep study because of the complexity, I mean, of the model. And but my question is, did you think, or did you plan to look at more kind of spiking neural networks domain, or rather you? I mean, is there any particular reason that you chose this specific mathematical model for neurons and not going for spiking, for example?
I think a lot, like, we're both very much aware of Chris Elias-Smith and his lab's work at Waterloo, and we're both big fans of that work. We are kind of trying to do something very similar, but we are less, I guess, committed to the nitty-gritty details of neuroanatomy and simulating those low-level details. I guess I think our more focus is on kind of a model that will be easier to scale up to very large tasks. So we are doing something very similar, and we are absolutely going to be cribbing from Elias-Smith's lab and all of the researchers that worked with Nengo and the Nengo framework for ways of kind of solving some of these problems.
And I would say, to piggyback off of what Alex was saying, you have a spectrum. You have ACTAR and SOAR on one end, which is very high level cognitive modeling with some explanations. There's millions of variations. And then on the other end, we have Ningo, for example, as an incredibly low-level spiking neural implementation. We like to think of where our architecture falls in the middle as a bridge between the two, because the idea is that we're trying to emulate certain aspects that are in high-level cognitive architectures already, like ACT-R, but also connect it better to the neural substrate, which is what Ningo does, but again, at an incredibly low level, and you're not typically necessarily modeling the interaction between these components that often. However, if Alex, if you go a few more slides, there's a couple bonus slides I had in case this one, in case such a question was asked. So Evgeny, that was a very good question. So it turns out that we also have work on how that neural generative coding model can be implemented from a purely spike train perspective. Actually, the work below came out in 2019, which was inspired. I went to one of the neuroscience camps and learned the inner workings of Ningo and how to model spike trains and more interesting models of neurons like the Hodgins-Huxley model and I always forget how to say it, the Eshkovich model. I'm not saying quite right, but I focused on the leaky integrate and fire model. And that's what that work in 2019 shows, is it basically shows how to take that architecture I explained earlier in this talk and formulate it for spike trains, which is actually very interesting. It's very similar design. The only difference is now the sparse codes that come from binary spikes, which we're modeling from a potential threshold. You can actually model the voltage potential and the electrical currents in the system. You box that up into the neural state. The idea is this neuron is now aware of its own buildup, and then it will fire a spike when it reaches a threshold, and then we can add a refractory period and all the nice things that you like in a spike train model. And what's neat is you have to deal with what's complicated is how do you create the learning signal? Because I explained that you have error neurons that actually compute a mismatch. And you could work with the binary signals directly, but it turns out that real spike trains are very sparse and they're temporal. So, they're going to be representing an image over time. What a neat trick that we did in that 2019 paper is basically we took that idea of the error neuron and said, well, wait a minute. We usually apply a low-pass filter anyway. That's what Ningo does when it models spike trains to create a sort of like a rate-graded coding or a continuous approximation of what's going on with those spike trains. So if we use the low-pass filter or a variable trace, which is often done to do spike time-dependent plasticity, the idea is that we can actually create that real-valued signal, and now you have at every time step that rough error neuron value that I'm looking for. And now you can adjust the synaptic weights almost the same way as I explained in this talk, except you have to use now those low-pass filters applied to the spike trains to generate the right, the continuous valued reality of those spike codes. This was also inspired. I've also read a lot of Randall O'Reilly. You might have heard of him in the work on PDP++. And so there was a lot of interesting discussion in one of his big textbooks where there's a mapping between you can work in the spike train level and you can flip the architecture towards the rate-graded coding, and the idea is you can just calculate a certain equation and you collapse all the spike codes within a time window to a real valued approximation. And we just say we're learning at that scale, but if we unzip it, you kind of get back to the low-level spikes. So what's nice about that 2019 paper I'm sort of pitching is that's the bridge that gets us down to the spike train model. So if our architecture can work at the vector symbolic kind of rate coded level that we're proposing now, which already has a time scale. Like the fact that neural generative coding is stateful already simulates what's going to end up happening one more level below. It's just now the number of steps to simulate time are going to be greater because now we're dealing with very sparse codes that are temporally dependent as well. And so it would work. It's compatible. And I would say that this would allow us to then, you could imagine writing an alternative version or a lower level version using the framework. We called that model the spiking neural coding network, which gave an example of how to learn that generative model, but purely through spike trains and that little variable trace low pass filter trick I explained. So it's not incompatible with that too. And probably future work could go one step lower, and then you almost get to where Ningo is doing, but its own perspective. And it has its own commitments and theoretical principles that would be a little bit different. But
all right, thank you. Anybody else who has a question?
Yeah, I had a couple of questions.
No, go ahead, Tony.
Yeah, so very, very interesting and ambitious work. You're covering a lot of stuff here. I really like the idea of trying to combine the control of a system like ACTAR with the neural approach. So one really quick question I had was the AGNC work. What's the best reference to look at to get a good sort of intuitive idea of how and why that works?
yeah, so we do have it. I don't think we have our reference slide in here. I can put the link in the chat to the paper. It is available on arXiv right now. It's currently under review, but I can put that right away. It's called Backprop-Free Reinforcement Learning. I'm going to put it on the chat now, and hopefully this would be where we proposed it. So, and that's where all those results that I demonstrated come from. Do you see that link?
Yeah, I do. That's okay, great. Yep, okay, thank you. Yeah, and then the second question I had was, you were talking about the concept's memory vector being the sum of all the questions to which that concept is an answer. And again, I think I've thought a lot about how you could, that the vector for something should be, it should be related to the things that it's about and answers to. But the way you formulated that seems almost unbounded, like it needs some constraints. And because I could say, okay, a horse that could be an answer to the question, what doesn't have 3 legs? What doesn't have 5 legs? What doesn't have 6 legs, etc. You could get ridiculous. But a couple of ways I could think of constraining that would be, you could do, well, it's an answer to the questions that are encountered and perhaps weighted by probability, or you could, go ahead.
Yeah, it's that. It's to be more precise, it is specifically informed by experience. So it's only going to be the associations that are encountered, which would be a better, more careful way to phrase it.
Yeah, okay. Yeah, there's another way I was thinking that could be interesting to approach that, was that if you can draw a parallel to like some sort of relational database system, and then you say it is the answer to certain kinds of queries that you could formulate in that system. Again, you'd have to limit it, but that was the other way I was wondering whether you could constrain that. Okay, thank you.
Yeah, so it's constrained by experience, and it because we want it human-like, it is also constrained by probabilities.
Okay, thank you, Alex. Anybody else who wants to ask a question to the presenters?
I have a short one.
Yeah, go on then.
Just kind of follow up on your point about the crystallized spawn architecture. So I was just thinking, so we know that the architecture there and it works. And I was wondering, what do you think, guys, you would add to the, like, what would be there on top of it once your proposal is implemented? Would it be more that the neural predictive coding is like a better, like a learning model? Or what would be what would be the pros of that model, right? What is the addition of integrating these two frameworks now, holographic or like vector symbolic architectures and predictive coding?
That's a very good question. And yeah, actually, in your question is part of the answer. So the motivation, even before we got into combining it with declarative memory, one of the ways that I learned that, at least at the time, this was again 2019, 2020, it might have changed, but Nango often learns offline. And the way it seems like what that simulation tool is used is they solve for the weights between, for example, different layers. And they use some really amazing and clever linear algebra tricks to make this work, called encoder decoders, which it might sound like a neural net thing, but it's actually more of a linear algebra trick where they actually decompose a matrix connecting maybe two layers in a certain way. And what they do is they solve an offline optimization problem to find those weights. And then you initialize them in your architecture, and now you can simulate based on like certain tuning curves and other properties of spike trains. And the other mechanism, they do have some online learning, but it's often based on a form of like spike time dependent plasticity and Hebbian learning, which isn't necessarily bad. But the thing is that when they use, for example, when they try to do supervised learning tasks, they end up resorting to, again, another part of their framework, which is you train a backpropagation-based network, and then they have this really clever process of converting it to a spike train, and now you can use this massive classifier in their system, whereas the neurogenerative coding framework by itself lends a complete, kind of a different way of learning. I wouldn't say completely different. It offers error Hebbian-based learning. So what's kind of neat is that now we're having neurons generate their mismatched signals. So when one layer tries to predict the state activities of another, you're going to get that mismatched signal, like I said, for free. And now you can actually use the original post activities multiplied with that, and you get an error Hebbian rule to adjust those signals. The other thing is that these signals also affect the state value. Now, again, Elias Smith's work is focusing on the other, there's like a whole class of spiking neural nets, a galaxy of them actually. And he's kind of focusing on more the feed-forward style model, which is, again, you have like a modeling voltage potential and electrical current. And he does have, Ichkovich neurons and other things like that that you can play around with. But the idea is that they're driven by input stimuli, whereas if you wanted to learn like a top-down directed generative model of this framework, that would be extremely difficult, if not possible, from the way I learned in the neuroscience camp to use this tool. So that was one big issue. So it offers kind of a different framework for learning that is ideally suited for streams. So neurogenerative coding can be competitive. And if you look at, there's another paper, I'll try to post that also in the link if for those that are interested, the generative model paper, Ororbia and Kiefer 2020, that shows how to learn this on like generative modeling data sets. That one shows like an equivalence or a competitiveness, let's say, with backpropagation, which was very satisfying just to say, hey, it can scale as a machine learning task would, and that's really nice. But the ideal scenario for neurogenerative coding is literally for streams, which is not necessarily the focus of a lot of deep learning. So the idea is you have a robot and it's processing sensory input. You get that input one time, you'll never get it again. Do something quickly with it, build a representation, and constantly adapt. The neurogenerative coding model, in some sense, should never be turned off. The idea is that these neurons should constantly adapt to non-stationary input pattern streams. So that fundamentally is where I think this framework is best suited. And I've done some work on online experiments, but the idea is that if you actually put that as the forefront learning mechanism, that's not necessarily ideally what Elias Smith's spawn architecture or Nango is meant for. One other part that I liked, but also found a criticism in his framework is he also has a beautiful basal ganglia model and other models that are built from like the spike level. So it's not to say we're the first to think about, building, neuro anatomically even partially correct, even at a high level of the basal ganglia. But the way that they did multiple tasks in their architecture, their spawn architecture, is the task selection framework is kind of human supervised. It's not learning automatically how to distinguish between tasks. And it's kind of designed in a way that they care more about, I want to show this experimental result. If we had a task selector model that was predisposed and pre-designed to say, I know that task A and task B are different, it's going to know which part of the spawn architecture to turn on, shut off. And I asked this question, I actually probed them saying, well, is there any mechanism for this to adapt itself? Can the basal ganglia train itself? And the answer is no, but that's not the experimental stuff that they were interested in looking at. Whereas the work that we've pushed, for example, in the lifelong learning results, that basal ganglia learns to separate and design tasks itself. Now, again, another level that Elias Smith looks at, which more from the task application level as opposed to the modeling level, they're looking at like maybe certain psychological tasks, and they kind of look at like, I think they looked at the Wei-Sun card task and a couple other things, but they say, well, their answer to me when I said, well, what if our system needs to decide what task is it operating in? They'd say, well, a psychologist would tell you what task you're doing. It's going to say, we're doing the Wei-Sun card task, let's do that. And the basal ganglia oriented system will just know what to do for that. And that's where the human signal came in, the human arbiter, the homunculus. Whereas our system would say, well, look, as long as I was trained on samples from a task that's either similar or that task, I can now detect automatically in the future, I need to allocate these resources within our neural cognitive system to approach this particular task. And I usually use classification as a simple example, but that's where our results currently show. It's like, well, I trained it on different distinct classification tasks. And when I showed it more cat and image dogs later on, the idea is that this thing could actually say, well, look, I've seen that before, so I know it's task 1, even though I might not call it the cat dog task. And it'll actually say, let me pull those resources again, and I can adjust those neurons, and I'll actually improve my classification performance as opposed to just, oh, I'm going to override and just only remember these current tasks, because it'll learn to extract the right features. So that's kind of what we offer from the neurogenerative coding side, a streaming, adaptive, continuously adaptive learning framework, kind of using the predictive processing theory to ground us through error Hebbian learning. And the other thing is that our system, the way it's designed, is that it's learning automatically how to allocate these tasks, as opposed to, we could have a mode in our cognitive architecture where you could hard code things as well, like any good experimental system would. But the idea is that the system is meant to sort of figure out on its own what task is it actually operating on and what resources to pull for it. So that's another thing we are addressing, whereas from my current understanding of SPAWN, that's not their focus or their interest at the moment either. They're not interested in dealing with catastrophic forgetting or lifelong learning either.
They also, I guess, have, I think if they have a declarative memory, it's an offline one. I'm not sure that they have one. I don't remember.
I have a thought maybe to share with you rather than a question. Over the past 2 years, maybe several works on context-based learning or multitask learning, which uses context vectors, appeared. And for example, one of the works was presented from Abba's group before in the seminars. So another one is from Berkeley group. But what I'm thinking, it would be interesting to study this generative models, maybe in combination with these proposals, because people, I mean, to me, when I read these articles, I mean, previous works on context vectors, it was always a question. So how can one get a context? So, and it appears that it's kind of natural source of context. I mean, that can come from your model. Well, just as a side thought. Another thing which would be interested, but I mean, we can discuss offline over the emails or something. I mean, I understand that maybe it's part of your future or current work, but what would be interesting is to see the properties of these learned representations in your model. So, I mean, really, so how these different dogs look like. I mean, as part of recall and stuff. So it's kind of intriguing to me.
I do have a tiny taste of that actually for something not in the cognitive. Alex, if you mind, can I share my screen?
Sure. my only thought on context vectors is they are another way of getting around the catastrophic interference problem, or can be. And in a sense, we could almost think of maybe the basal ganglia as sort of a context vector. I don't know.
Well, yeah, I don't know what, Evgeny, what do you think of that? But I also have
no.
Go.
No, I don't have any any good comment on that.
So if those that are still here, let me share my screen. It's from hot off the press, like literally this week. Can you see my screen?
Yes.
Okay, so let me try to zoom in here. So I actually did look at, so actually that the Ororbia Kiefer paper, we've had to do more revisions and updates. So one question was asked is what's actually being learned in the representations of a, let's say, 3-layer version of that model trained on digits. So and again, this is now not in the lifelong learning setting, this is just one task. But what was really interesting is that when I did try to figure out some scheme to actually visualize what's going on, for those of you that have heard of sparse coding, it turned out that the lowest level of the neurogenerative coding network that I designed for just learning to sample and synthesize and dream up of digits, when it was trained on a big database of like 0s, 1s, 2s, 3s, 4s, whatever, I'm showing here a 0. It looked like what the bottom level learned was visual stroke features. And again, this is a little bit of a stylized diagram, but it is taken from a trained model, I promise you that. And it looked like the bottom level learned like pieces of curves, and of course it had other features that were shut off. And the reason why I invoke the notion of sparse coding is that the idea is that a lot of features are going to be 0 or so close to the value of 0 that they're just deleted. The network is not using it. What the upper layers appeared to learn is when I tried to convert them into a map, they don't learn other features or things that look visually interesting to our eyes. They learn what look like blueprints or command points. And the neurons that are shown here that are like really white were the highest activated neurons from level 3 saying, I want to turn on these neurons in layer 2. So it was like a latent command structure. And it said, look, I want these highly activated, and actually had a coefficient assigned to them as well. I'm not showing that coefficient here. It would say, these are turned on with a very high coefficient. And we looked at like the top 30 ranked coefficients. And it says, these are what I'm going to use in layer 2. And then layer 2, if you look at the filters of those activated neurons, they also have blueprints for layer 1. And they say, I'm going to turn on these, and I want to use this combination. And of course, if you look at layer 1's filters, they're just literally the visual dictionary. And what it does is it's learning like a hierarchical composition. It's learning to say, I want to mix and match these things for a particular input that I want to reconstruct. So this 0 at the very bottom is actually the produced superposition of those low-level features and the coefficients that the upper 2 layers managed to spit out, because I wanted to see, could I manually construct the digit 0 from actually a weighted superposition of those low-level features. It was really neat because it worked. And then we have one more table at the bottom. Again, we just took specific samples. We didn't do like a general analysis. You can see the original 0 to the very far left. Of course, I have the class label, the superposition, the weighted superposition that I took with those weighted coefficients. And here I'm just showing like the top 11 highest ranked things. There was about 30 or so, or 35 before those coefficients got so small that the rest of the neurons were turned off. There was like about 400 neurons or 316 neurons in a given layer. And so you can see that actually they are learning to compose those features together. Not all the features are just distinct curves. Some of them look nice like that, but you can see it's taking ghostly pieces of other 0s and saying, well, this seems to be really good for capturing a lot of the other variation in the data set. And what's neat is if you scroll down, I mean, not all the filters are perfect. There's a couple that are seemingly strange, but the weighted superposition kind of clears that out. And you get, like, for example, that 4, even though we have this kind of strange filter there, but maybe the weighted superposition of the rest kind of drown it out. And you can see, for example, that it even composes a 9 and an 8 from just those low-level features. However, those coefficients and which of those features are selected come from the latent command structure above. So that gives you a taste, at least. I mean, there's always more work to be done, but we did examine very, very recent, like literally like last week, what those latent features might actually look like to give a kind of an intuition of what's going on. So it seems like that's what the neurogenerative coding model is. And when you're training it as, let's say, a modality cortex, like I'd argue you could roughly pretend this is like a neurogenerative visual cortex, right? So those features are specific to the digits that it was exposed to. What would it look like when it starts to get mixed with a motor cortex? What would it look like when it's starting to get mixed with a working memory or some other model? That, well, would be very interesting to see if it would change, if the working memory would start, maybe offloading some of that structure. I don't know. I don't know how these big pieces of memory would start to work together. But ideally, you'd imagine the working memory might store maybe a template, is what I could imagine, like maybe one of these command templates, and it can say, hey, use this to trigger these neurons. But we would also want to store that very compressed, because these are very sparse codes if we look at the original figure, only a few. And again, the white neurons are like the ones that it thinks are the most important, and the gray ones are kind of involved, and black means not part of this. And you could imagine that extremely compact code could go into like declarative memory or some other part of memory for long-term storage and then retrieved when it's relevant. So again,
it definitely answers my question. Is this paper published or it's work in progress?
This paper is on archive. It's still under review. This result is in response to some reviewer requests. So
okay.
It'll come out. But I can give you the link to this as well, actually, in the chats.
Thank you. So we have probably room for one more question before we close this session.
I just put the link, by the way.
Yes, thank you. That's great.
Yeah, maybe something very short. This was, of course, a talk full of details, and I certainly haven't got anything. Anything, not too much. So now what I wanted to say is, if learning is concerned with adapting expectations, a very old guy comes into my mind. This is Jean Piaget, who worked about the equilibration theory, which more or less says if you experience an input which really deviates from your expectations, then you try to modify something. I know how it is written, horrible, and it's of course not formal, but I thought the model you presented might be a kind of mechanism which somehow is coherent with what he says. Okay, not talking about equilibrium, of course. He's not a physicist, he was a zoologist, huh? But I wondered if this idea, whether these two things, your approach and Jean Piaget's idea of equilibration have anything to do with each other.
I mean, not directly was I motivated by it, but yes, that concept. Because I mean, there's also Helmholtz's old ideas as well. That I didn't necessarily read that to say, oh, I'm going to build the model based on what he said, but that idea is embodied here. So you could imagine when you're saying equilibrium. I know that that's a careful word to be careful, and I don't want to say it's the physics equilibrium, but you could imagine that with this generative model that I was talking about, just to even keep the simple one, I give it an image. I don't know what the neural activities would be to explain that image, but I would make a prediction, it'd be garbage at the beginning. Well, when we do that correction cycle, you have to take many steps. It's like, I got to look at the image, I make a new prediction, I'm still off, I keep adjusting. And of course, all the other layers inside are doing the same thing with their nearby layers. They're trying to say, well, wait, this state I'm predicting, that's wrong. I'm going to correct myself and offer a top-down pressure. So the system ends up cycling through. And you could argue that what it's finding is, I'm going to put quotes, equilibrium, right, for each image, because it's trying to find an attraction point to say, this is good. When I reach this image, these activities yield very low prediction error across all the activities, or the sum of prediction errors, if you will.
And maybe, I don't know whether Alex would agree that this kind of task, equilibrium point or so, would come from declarative memory, maybe, I don't know. Because if it is stored in some sense there, and the cue comes in, which fits perfectly to what is already present in the declarative memory, then everything is fine. So the memory is more or less a kind of zero, huh? More or less. Okay, then
I would almost kind of like the declarative memory model that we're proposing here is has a bunch of memory vectors. You know, kind of think of the memory vectors as attractors that things will kind of gravitate towards, though they are moving attractors because the memory vectors do get updated.
No, that's a very nice picture. And as a physicist, I like this picture a lot. Yes, right. Of course. Thank you.
Yeah, I think it's a really cool concept to think about. Like, what I did, for example, in the neurogenerative coding, the second linked paper or the visual diagram, is we take about like 50 steps per image to do that cycling to find the latent activities. Of course, you could also appeal to another well-known statistical framework, expectation maximization. The idea is that we have latent variables. We want to first maximize or find the actual activities that explain the input, and then we adjust the parameters so that we next time will get there faster or get a better representation the next time. And the neat thing about that EM framework that I would argue is similar to equilibrium is you'd say, well, what our model is searching for is an equilibrium point, or, you could also say, well, it's technically a maximum a posteriori estimate of the distribution of that latent activity. It's not specifying the whole distribution because that's really hard, but finding this one code at every layer. And we say, hey, look, our system minimizes its free energy, its prediction principle. And the free energy from Carl Friston also gets another connection back to statistical mechanics and equilibrium, because you'd say, well, we're minimizing free energy at the end of the day, and then that's connecting to variational inference and Bayesian inference. But I think the other neat thing is you could imagine, well, what if I ran that model for a really long time? Because you could keep going. You could probably even theoretically show that it converges to like an equilibrium distribution or something roughly at every layer when you run enough cycles. Again, like I don't know if you've heard of a Boltzmann machine, where you have to like use Monte Carlo sampling or Markov chain Monte Carlo to get to like an equilibrium distribution. There's probably another connection like hidden in here, then that's what's going on with this error correction process. The other nice thing that I would say complements it is in the paper I linked, although there's more improved results going to be, I'll update, by the way, that archive paper very soon, so associative memory, and if you think of Hopfield networks, right, that's also using attractor points and saying, hey, when I'm completing a pattern, this guy is really close to this attractor point that I stored in my Hopfield network. One thing that we did with the neurogenerative coding paper, neurogenerative coding model in that paper, is we did pattern completion, where we gave it an image and covered half of it. And we said, go ahead and finish it for me. And we never trained it to do this. We just trained it again the way I was explaining, predict the input, adjust your latent causes and be done. And then at test time, what we did is we use that inference cycle. We just don't adjust the weights. There's no more learning. We turned it off. And what we found is actually it was pretty good at completing those images. It wasn't perfect. There was a couple of weird ones. And the explanation for that, the reason why, because the reviewers in our one paper said, well, how, if it wasn't trained to do pattern completion, how did it do it? And the argument is that because it's still doing that correction process and saying, well, for the unclamped variables at the input, I get to modify them however I want. So what it's doing is it's doing like a search, and it's saying, well, which of those patterns that I exposed to look most like that? And I think that's what it's doing, some kind of attractor. And it says that's very similar to the zero. So I'm going to complete it that way. It's probably not exactly what we wanted, because there is, there is error. We measured the error, there was a little bit off, but it still looked like a zero visually. And you're like, well, that wasn't so bad. And I think that adds another point to that equilibrium idea, that there is something that it's doing where it's finding attractor points or pins and saying this sample is really similar, and that's the auto-associative aspect of the model.
Very nice. Thank you so much.
Yeah, thank you. It's a good question.
So I want to thank you a lot, Alex Kelly and Alex Ororbia, for being with us today. So great talk and lots of things to think about. I suggest we move the discussion offline. So definitely I have in mind one question to ask you later on. So once again, thank you very much for this talk. So we meet again on our webinar in 2 weeks from now. So, and by this we end this meeting. So thank you.
Thank you very much for having us.
Yeah, thank you for having us, and
Thank
thanks
you
everyone
very
for
much
attending.
for the talk. Thank you so much.
Thank you,
Bye.
guys.
Bye.
Bye-bye.
Thanks for the question.